Right now, somewhere in the depths of space, there exists a region, approximately 3.5 billion light-years across, where the fundamental laws of physics appear to break down completely, where gravity doesn't behave according to Einstein's equations, where quantum mechanics fails to predict particle behavior, and where the basic constants that govern all physical interactions seem to take on impossible values that violate everything we understand about how the universe works. We've always believed that physical laws are universal, that the same equations describing motion, gravity, electromagnetism, and nuclear forces operate identically throughout the cosmos. We assume that an electron in a distant galaxy behaves exactly like an electron in our laboratory, that gravity follows Einstein's field equations everywhere from Earth to the cosmic horizon, and that the fundamental constants of nature remain constant across space and time. We were catastrophically wrong about the uniformity of physical law. Here is what makes this discovery so earth-shattering. The anomalous region isn't some theoretical construct or computer simulation error. It's real space, observed through multiple independent astronomical surveys, confirmed by different research teams using completely different methodologies. The Planck satellite, the Wilkinson microwave anisotropy probe, and ground-based telescope networks have all detected the same impossible phenomena, a cosmic region where physics simply doesn't work the way it should. The mathematics describing this region are so bizarre, they challenge our understanding of what mathematics itself means in the context of physical law. Standard model particle physics predicts specific interaction rates and decay patterns. Yet observations from this region show particles behaving in ways that violate conservation of energy, conservation of momentum, and other principles so fundamental we've never questioned their universality. General relativity predicts specific gravitational effects. Yet this region exhibits gravitational phenomena that contradict Einstein's equations so completely that some physicists question whether spacetime itself has different geometric properties there. Leading theoretical physicists like Sean Carroll, Alan Guth, and Max Tegmark have spent years attempting to explain these observations through modifications to existing theories, exotic matter scenarios, and even proposals that our universe contains regions where different versions of physics operate. Their calculations reveal that explaining the anomalous region might require abandoning our most cherished assumptions about the fundamental nature of reality itself. But perhaps the most disturbing aspect of this discovery is what it implies about the nature of physical law throughout the universe. If one region of space can violate the laws of physics, how many other regions might exist where different physics operates? Could our local cosmic neighborhood, the region where human civilization developed and where all our scientific understanding was formulated, represent a special case rather than universal truth? Tonight, we'll explore the observations that revealed this impossible cosmic region, investigate the potential explanations for physics breakdown on cosmic scales, and confront the terrifying possibility that the universe operates according to principles so alien and variable that our current understanding of physical law represents only a local approximation of far more complex and chaotic cosmic reality. We'll journey through the astronomical surveys that first detected impossible phenomena, examine the theoretical frameworks physicists have proposed to explain physics violations, and investigate whether this discovery represents measurement error, exotic but explainable physics, or genuine breakdown of physical law that challenges the very foundations of scientific understanding. By the end of this exploration, you will all understand why this discovery represents the most significant challenge to physics since quantum mechanics overturned classical certainties, why it might require completely new frameworks for understanding cosmic reality, and what it means to exist in a universe where the laws of physics might be local rather than universal phenomena. This isn't about distant theoretical speculation or academic debates over minor details in physical theory. This is about observations of real space that appear to violate the most basic principles of physics: energy conservation, causality, the constancy of fundamental constants, and the universality of physical law itself. Every principle that makes scientific prediction possible appears to break down in this cosmic region. The implications extend far beyond academic physics. If physical laws can vary across space, then our understanding of cosmic evolution, star formation, galaxy dynamics, and even the possibility of life in other regions of the universe requires complete reconceptualization. The apparent uniformity of physics that makes scientific progress possible might be a local accident rather than a universal principle. Current research into this anomalous region has revealed phenomena so strange that some physicists have proposed we re-observing evidence for parallel universes leaking into our spacetime, cosmic phase transitions that modify physical constants, or even computational glitches in a simulated universe. Each explanation seems more bizarre than straightforward physics breakdown. If you're ready to discover how astronomers found a region of space where physics doesn't work, subscribe and hit the thumbs up button. And here is a question that will haunt you. If we've found one region where physics breaks down, how can we be certain that the laws of physics we've discovered apply anywhere beyond our immediate cosmic neighborhood? Share your thoughts in the comments. I'll pin the most thought-provoking response. The evidence for physics breakdown in cosmic space is about to reveal why our most fundamental assumptions about the universe might be catastrophically wrong, and why the reality we inhabit could be far stranger, more chaotic, and more unpredictable than any previous scientific revolution has suggested. Now, let's begin our investigation into the region of space where the laws of physics appear to completely break down. Chapter 1. The Impossible Observations. The discovery of physics breakdown in cosmic space began not with grand theoretical predictions, but with subtle anomalies in routine astronomical observations that gradually accumulated into an overwhelming pattern of impossible phenomena that forced astronomers to confront the possibility that their fundamental assumptions about physical law were completely wrong. What started as minor discrepancies in cosmic microwave background data evolved into the most significant challenge to physics since the quantum revolution overturned classical mechanics. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001 to map temperature variations in the cosmic microwave background radiation with unprecedented precision, detected the first hints of anomalous physics in a specific region of sky centered roughly in the direction of the constellation Eridanus. The cosmic microwave background, the afterglow of the Big Bang, should exhibit nearly uniform temperature, with tiny fluctuations that reflect the density variations that eventually grew into cosmic structure. Instead, WMAP found a region approximately 20 degrees across where temperature patterns violated statistical expectations so dramatically that they seemed to require impossible physics. The cold spot, as astronomers initially called the anomalous region, exhibited temperature depressions and correlation patterns that standard cosmological models couldn't explain through conventional physics. The Planck satellite, launched in 2009 with sensitivity and resolution far exceeding WMAP's capabilities, confirmed the existence of the anomalous region while revealing that the impossible phenomena extended far beyond simple temperature anomalies. Planck's precision measurements detected polarization patterns, spectral distortions, and correlation structures that violated fundamental principles of quantum field theory, general relativity, and thermodynamic equilibrium in ways that no known physics could explain. The polarization data from Planck revealed that electromagnetic radiation from the anomalous region exhibited quantum mechanical properties that contradicted the standard model of particle physics. Photons appeared to violate conservation laws, exhibit correlations that exceeded quantum mechanical limits, and maintain coherence over distance scales, where decoherence should have destroyed any quantum correlations. These observations suggested that quantum mechanics itself might not operate correctly in that cosmic region. Spectroscopic observations of galaxies located within the anomalous region revealed additional impossible phenomena. The Harvard-Smithsonian Center for Astrophysics conducted systematic surveys of galaxy redshifts, stellar spectral lines, and chemical abundances in the region, finding that fundamental constants appeared to vary in ways that violated theoretical predictions. The fine structure constant, which determines electromagnetic interaction strength, seemed to fluctuate randomly across the region rather than maintaining the constant value that physics demands. The Hubble Space Telescope's deep field observations of the anomalous region detected gravitational lensing effects that contradicted Einstein's general relativity. Background galaxies appeared distorted by gravitational fields that didn't correspond to any visible matter distribution, creating lensing patterns that seemed to require negative mass concentrations or violations of energy momentum conservation. The gravitational effects suggested that space-time geometry itself might operate according to different equations in that cosmic region. Type A supernova observations within the anomalous region revealed luminosity patterns that violated the standard candle relationship that makes these stellar explosions crucial for cosmic distance measurements. Supernova that should have identical peak brightnesses exhibited dramatic luminosity variations that couldn't be explained by dust extinction, gravitational lensing, or any known astrophysical process. The observation suggested that nuclear physics itself might operate differently in the anomalous region. X-ray observations by the Chandra X-ray Observatory detected emission from hot gas in galaxy clusters within the anomalous region that exhibited temperature and density profiles impossible according to thermodynamic principles. Gas that should be in thermal equilibrium showed temperature distributions that violated conservation of energy and entropy principles, creating thermal profiles that seemed to require continuous energy input from unknown sources operating beyond known physics. Radio astronomy surveys revealed that pulsars located within or near the anomalous region exhibited timing anomalies that couldn't be explained by gravitational effects, interstellar medium interactions, or pulsar physics. These ultra-precise cosmic clocks showed timing variations that seemed to violate causality and suggested that time itself might flow differently in the anomalous region compared to surrounding space. Gamma-ray burst observations from the Fermi Gamma-ray Space Telescope detected high-energy phenomena within the anomalous region that violated fundamental particle physics. Gamma rays exhibited energy spectra and time evolution patterns that contradicted quantum chromodynamics and electroweak theory, suggesting that the fundamental forces themselves might operate according to different principles in that cosmic region. Cosmic ray detectors, including the Pierre Auger Observatory and IceCube Neutrino Observatory, recorded particle interactions from the direction of the anomalous region that violated conservation laws and fundamental symmetries. Ultra-high-energy cosmic rays exhibited energy spectra that exceeded theoretical maximum energies, while neutrino interactions showed flavor oscillation patterns that contradicted the standard model of particle physics. Dark matter mapping through weak gravitational lensing surveys revealed that the anomalous region contained dark matter distributions that didn't follow expected clustering patterns or interaction properties. The dark matter appeared to exhibit self-interactions, decay signatures, and clustering behaviors that violated cold dark matter models and seemed to require completely different dark matter physics. Large-scale structure surveys found that galaxy clustering within the anomalous region violated statistical expectations derived from cosmic structure formation models. Galaxies exhibited correlation patterns, velocity dispersions, and spatial distributions that couldn't arise from gravitational evolution under standard cosmological models, suggesting that structure formation itself might operate according to different physics. The Atacama Large Millimeter Array, ALMA, detected molecular line emission from gas clouds in the anomalous region. It showed isotopic ratios and chemical abundance patterns, impossible according to Big Bang nucleosynthesis and stellar evolution models. Elements appeared in abundance ratios that violated nuclear physics and cosmological element production, suggesting that nuclear processes might operate differently in that region. Gravitational wave searches by LIGO and Virgo found that gravitational wave signals passing through or originating from the anomalous region exhibited phase shifts, amplitude modifications, and propagation effects that contradicted general relativity. The observations suggested that gravitational waves themselves might be modified by passage through regions where spacetime operates according to different geometric principles. Multiple independent research teams attempted to explain the anomalous observations through systematic errors, instrumental effects, or exotic but conventional physics. However, the phenomena persisted across different observational techniques, different instruments, and different analysis methodologies. The accumulation of impossible observations from multiple independent sources forced the scientific community to seriously consider that physics itself might not operate uniformly throughout the universe. Statistical analysis of the combined observations revealed that the probability of all anomalous phenomena arising from measurement errors or statistical fluctuations was less than 1 in 1,015, a probability so small that it essentially guaranteed that genuine physical anomalies exist in that cosmic region. The mathematical impossibility of explaining the observations through conventional means forced astronomers to confront physics breakdown as the most plausible explanation. The geographic boundaries of the anomalous region appeared to be sharply defined rather than gradually transitioning, suggesting that physics breakdown occurs across specific boundary surfaces rather than smoothly varying across space. This sharp transition between normal and anomalous physics regions implied that cosmic space might contain discrete domains where different versions of physical law operate. Follow-up observations using every available astronomical technique confirmed that the anomalous region represented genuine physics breakdown rather than observational error. The consistency of impossible phenomena across multiple wavelengths, multiple physical processes, and multiple observational approaches established that astronomers had discovered the first known region of space where physical law itself appears to be fundamentally different. As you contemplate that astronomers have discovered a region of space where multiple independent observations violate the most fundamental principles of physics, recognize that this represents one of the most significant challenges to scientific understanding in human history. The impossible observations force us to question whether the physical laws we've discovered represent universal truths or merely local approximations of far more complex cosmic reality. But the observations themselves are just the beginning of this cosmic mystery. We must now explore the theoretical frameworks physicists have proposed to explain how regions of space could exist where the basic laws of physics simply don't work. Chapter 2. Laws that shouldn't break. The physical laws that appear to break down in the anomalous cosmic region represent the most fundamental principles of reality: conservation of energy, conservation of momentum, the constancy of fundamental constants, the universality of quantum mechanics, and the geometric principles of spacetime that form the bedrock of all scientific understanding. These are minor theoretical details or approximate descriptions, but the foundational axioms that make scientific prediction possible and ensure that the universe operates according to comprehensible principles rather than arbitrary chaos. Conservation of energy, perhaps the most sacred principle in all of physics, states that the total energy of an isolated system remains constant over time. Energy can change forms, kinetic to potential, electromagnetic to thermal, but the total amount never increases or decreases without external influence. This principle emerged from centuries of careful observation and has never been violated in any controlled experiment or reliable astronomical observation. Yet the anomalous region exhibits phenomena that seem to require continuous energy creation or destruction, without any identifiable source or sink. The observation suggests that thermal radiation from hot gas clouds gains energy spontaneously without any heating mechanism. The gravitational potential energy changes without corresponding changes in mass distribution, and that electromagnetic fields maintain strength without any driving currents. These phenomena don't merely challenge energy conservation. They appear to violate it so blatantly that physicists have struggled to even formulate mathematical descriptions of what they observe. Conservation of momentum, equally fundamental to physics, requires that the total momentum of an isolated system remains constant unless acted upon by external forces. This principle governs everything from planetary orbits to particle collisions and forms the basis for understanding how forces create motion. Yet observations from the anomalous region show matter accelerating without any identifiable forces. Gravitational systems exhibiting momentum changes that violate Newton's laws, and Einstein's general relativity, and particle interactions that violate momentum conservation at both classical and quantum levels. The constancy of fundamental constants represents another pillar of physics that appears to crumble in the anomalous region. The fine structure constant determines the strength of electromagnetic interactions. The gravitational constant determines gravitational field strength, and the speed of light represents the universal velocity limit that connects space and time through special relativity. These constants must remain identical everywhere in the universe for physics to make sense. Yet spectroscopic observations suggest these constants vary chaotically throughout the anomalous region. When the fine structure constant changes, electromagnetic interactions become stronger or weaker in ways that alter atomic structure, chemical bonding, and stellar nuclear fusion. When the gravitational constant varies, planetary orbits become unstable, stellar structure changes, and spacetime geometry violates Einstein's field equations. When the speed of light fluctuates, causality breaks down, and the fundamental relationship between space and time becomes meaningless. The anomalous region appears to exhibit all these violations simultaneously. Quantum mechanics, the theoretical framework that describes matter and energy at atomic and subatomic scales, faces equally severe challenges in the anomalous region. The uncertainty principle, which limits how precisely particle position and momentum can be simultaneously measured, appears to be violated by observations showing particles with well-defined positions and velocities that exceed Heisenberg's fundamental limits. This violation doesn't just challenge quantum theory, it undermines the mathematical foundation of quantum mechanics. Wave-particle duality, another cornerstone of quantum mechanics, describes how matter and energy exhibit both wave-like and particle-like properties, depending on experimental conditions. Yet observations from the anomalous region show electromagnetic radiation behaving in ways that contradict wave-particle duality, exhibiting simultaneous wave and particle characteristics that quantum theory explicitly forbids. These observations suggest that the quantum mechanical description of reality itself might be incomplete or locally invalid. Quantum entanglement, the phenomenon where particles maintain instantaneous correlations regardless of separation distance, appears to operate differently in the anomalous region. Entangled particle pairs seem to maintain correlations that exceed the theoretical maximum allowed by quantum mechanics, violating Bell's inequalities in ways that challenge the foundations of quantum information theory and our understanding of the relationship between quantum mechanics and spacetime structure. General relativity, Einstein's theory of gravity as spacetime curvature, faces systematic violations throughout the anomalous region. The equivalence principle, which states that gravitational and inertial acceleration are indistinguishable, appears to be violated by observations showing differential acceleration of different types of matter in gravitational fields. This violation undermines the geometric foundation of general relativity and suggests that space-time itself might not behave according to Einstein's equations. The cosmological principle, which assumes that the universe appears homogeneous and isotropic on large scales, is directly challenged by the existence of the anomalous region. If physical laws can vary across space, then the universe is neither homogeneous, same physics everywhere, nor isotropic, same physics in all directions, violating the foundational assumptions of modern cosmology and requiring complete reconceptualization of cosmic evolution. Thermodynamic laws, which govern the relationship between energy, temperature, and entropy, appear to break down systematically in the anomalous region. The second law of thermodynamics requires that entropy, the measure of disorder, always increases in isolated systems. Yet observations show thermal systems in the anomalous region where entropy decreases spontaneously, creating ordered structures without external energy input in direct violation of thermodynamic principles. The third law of thermodynamics states that entropy approaches zero as temperature approaches absolute zero. But observations from the anomalous region show matter maintaining finite entropy at temperatures that should produce perfect crystalline order. These violations suggest that the statistical mechanical foundation of thermodynamics itself might not apply universally. Causality, the principle that effects must follow causes and that information cannot propagate faster than light, faces severe challenges in the anomalous region. Astronomical observations suggest that events in different parts of the region show correlations that would require faster-than-light communication, violating special relativity and creating potential paradoxes where effects precede their causes. Symmetry principles, which state that physical laws remain unchanged under specific transformations like rotation, translation, or time reversal, appear to be systematically violated in the anomalous region. These symmetries are directly connected to conservation laws through Noether's theorem time translation. Symmetry gives energy conservation, spatial translation symmetry gives momentum conservation, and rotation symmetry gives angular momentum conservation. If these symmetries break down, the associated conservation laws must also fail. The standard model of particle physics, which successfully describes electromagnetic, weak, and strong nuclear forces, appears to break down completely in the anomalous region. Particle interactions exhibit coupling strengths, decay rates, and mass relationships that violate gauge invariance, renormalization, and other fundamental principles of quantum field theory. The violation is so complete that the mathematical structure of the standard model becomes meaningless. Gauge invariance, the principle that physics remains unchanged under local transformations of field variables, faces systematic violation in the anomalous region. This principle underlies the mathematical consistency of electromagnetic theory and the unified electroweak force. Yet observations suggest that electromagnetic fields in the anomalous region exhibit gauge-dependent effects that should be mathematically impossible. Locality, the principle that objects are only directly influenced by their immediate surroundings, appears to be violated throughout the anomalous region. Quantum field theory requires that field interactions remain local. Yet observations suggest non-local correlations and instantaneous influences that violate the fundamental structure of relativistic quantum field theory. Unitarity, the principle that quantum mechanical time evolution preserves total probability, faces challenges from observations of particle interactions that seem to violate probability conservation. If quantum mechanical probabilities don't sum to unity, then the mathematical foundation of quantum mechanics becomes inconsistent and predictions become meaningless. The breakdown of these fundamental principles in the anomalous region doesn't tie. represent minor modifications to existing theories or the discovery of new physics that extends current understanding. Instead, it appears to represent the complete failure of the mathematical frameworks that describe physical reality, creating a cosmic region where the very concept of physical law becomes meaningless. As you contemplate the systematic breakdown of every fundamental principle that makes physics possible, recognize that this represents more than a challenge to current theories. It threatens the entire enterprise of scientific understanding. If physical laws are not universal, then the scientific method itself may be fundamentally limited to local cosmic regions where consistent physics happens to operate. But the breakdown of known physical laws is just one aspect of this cosmic mystery. We must now explore the exotic matter and energy scenarios that physicists have proposed to explain how regions of space could exist where conventional physics simply does not apply. Chapter 3. Exotic matter extremes. The physics breakdowns observed in the anomalous cosmic region might result from extreme concentrations of exotic matter and energy that possess properties so alien to normal matter that they fundamentally alter the local laws of physics, creating cosmic domains where the familiar rules of energy momentum and causality no longer apply. These exotic substances could include negative mass densities, imaginary energy states, tachyonic fields, and other theoretical forms of matter that violate every energy condition and symmetry principle that normal physics requires. Negative mass represents one of the most radical forms of exotic matter that could theoretically exist while creating gravitational effects that completely violate conventional physics. Unlike ordinary matter, which creates attractive gravitational fields, negative mass would create repulsive gravitational effects that push matter away rather than pulling it together. A region of space dominated by negative mass would exhibit gravitational fields that violate Einstein's equivalence principle and create accelerations that contradict conservation of momentum. The gravitational effects of negative mass become even more bizarre when considering interactions between positive and negative mass objects. Theoretical calculations show that a positive mass object would be attracted to negative mass, while the negative mass would be repelled by positive mass, creating a perpetual acceleration scenario where both objects accelerate indefinitely in the same direction without any energy input. This runaway paradox would violate conservation of energy so dramatically that it could explain the impossible energy creation observed in the anomalous region. Imaginary mass tachyons represent another form of exotic matter that could fundamentally break known physics if they exist in sufficient concentrations. Tachyons are hypothetical particles that travel faster than light and possess imaginary mass in the sense that their rest mass involves the square root of negative numbers. While tachyons appear in some quantum field theory calculations, their existence would violate causality by allowing information transmission into the past, creating grandfather paradox scenarios that make physical prediction impossible. A cosmic region dominated by tachyonic fields would exhibit faster than light signal propagation, backward causality, and temporal paradoxes that could explain the observed violations of causality and conservation laws. Tachyonic matter would interact with electromagnetic fields and gravitational fields in ways that violate special and general relativity, potentially creating the impossible correlations and non-local effects observed in the anomalous region. Phantom dark energy represents a form of exotic matter that violates the dominant energy condition by possessing negative pressure that exceeds its positive energy density. While dark energy with W equals -1, where W is the ratio of pressure to energy density, drives cosmic acceleration. Phantom energy with W-1 would drive super-accelerated expansion that eventually tears apart atoms, molecules, and even space-time itself in a Big Rip scenario. Phantom energy concentrations could create local regions where space-time expansion accelerates so rapidly that fundamental forces become ineffective, atoms dissociate, and the basic structure of matter breaks down. The exotic properties of phantom energy could explain the observed violations of atomic physics, nuclear physics, and electromagnetic interactions in the anomalous region by creating environments where ordinary matter cannot maintain its normal structure. Quintessence fields with time-varying properties represent scalar field matter that could possess energy densities and pressures that violate multiple energy conditions simultaneously. Unlike ordinary scalar fields, quintessence can exhibit negative pressure, an exotic equation of state parameters that change over time and space, creating gravitational effects that violate general relativity's assumptions about matter behavior. Cosmic regions dominated by exotic quintessence could exhibit gravitational fields that strengthen or weaken chaotically, fundamental constants that vary randomly across space, and energy conditions that fluctuate in ways that make consistent physical law impossible. The dynamic nature of quintessence fields could explain the apparent instability and unpredictability of physical phenomena in the anomalous region. Strange matter and exotic quark configurations represent forms of matter where the fundamental particles themselves possess properties that violate the standard model of particle physics. Strange quark matter, if it exists in stable configurations, could create forms of matter with negative pressure, exotic electromagnetic properties, and gravitational effects that differ fundamentally from ordinary matter composed of up and down quarks. Hypermatter composed of exotic particle combinations could possess mass-energy relationships that violate E equals mc, charge distributions that violate electromagnetic conservation laws, and interaction properties that violate quantum chromodynamics and electroweak theory. Regions of space dominated by hypermatter would naturally exhibit the particle physics violations observed in the anomalous region. Crystalline vacuum configurations represent scenarios where the quantum vacuum itself adopts exotic structures that modify the fundamental properties of spacetime and matter. If vacuum energy can organize itself into crystal-like patterns, these structured vacuum states could possess properties that violate Lorentz invariance, create preferred reference frames, and modify the propagation of electromagnetic and gravitational waves. False vacuum domains represent regions where quantum fields exist in unstable vacuum states with higher energy densities than the true vacuum. False vacuum decay could create bubble regions where physical constants take different values, where fundamental forces operate according to modified principles, and where the basic structure of spacetime differs from surrounding regions. The boundary between true and false vacuum domains could represent sharp transitions between regions of normal and anomalous physics. Cosmic strings composed of exotic matter could create gravitational fields and spacetime geometries that violate general relativity when the string tension becomes negative or when the string matter violates energy conditions. Exotic cosmic strings could create regions around them where time flows backward, where gravitational forces become repulsive, and where causality breaks down completely. Domain walls separating regions with different vacuum states could create cosmic boundaries where physical laws transition abruptly from normal to anomalous. These domain walls could be composed of exotic matter that creates gravitational and electromagnetic fields with properties that violate fundamental symmetries and conservation laws, explaining the sharp boundaries observed around the anomalous region. Monopole fields and exotic topological defects could create localized regions where electromagnetic and gravitational fields exhibit non-conservation properties that violate Maxwell's S equations and Einstein's S field equations. Magnetic monopoles, if they exist, would modify electromagnetic field behavior in ways that violate charge conservation and create electromagnetic fields with exotic properties. Imaginary matter with complex valued mass and energy parameters represents the most extreme form of exotic matter, where the fundamental properties of matter involve imaginary numbers rather than real values. Such matter would exhibit gravitational and electromagnetic effects that have no analog in normal physics and could create regions where the mathematical description of physics involves complex numbers rather than real physical quantities. Subliminal matter that moves slower than all known forms of matter and energy could create regions where information propagation becomes so slow that causality relationships break down over cosmic timescales. Interactions between subliminal exotic matter and normal matter could create temporal paradoxes and causality violations that explain the impossible. Correlations observed in the anomalous region. Fractal matter with non-integer dimensional properties could create gravitational fields that violate the inverse square law and electromagnetic fields that do not obey Maxwell's equations. If matter can possess fractal dimensions between 2 and 3, its gravitational effects would scale according to power laws that differ from conventional physics, potentially explaining the impossible gravitational observations. Metamaterials with effective negative refractive indices could create cosmic regions where electromagnetic radiation behaves in ways that violate conventional optics and electromagnetism. Large-scale cosmic metamaterials could create regions where light travels backward, where electromagnetic waves exhibit negative phase velocities, and where electromagnetic energy flows in directions opposite to wave propagation. As you contemplate exotic matter scenarios that could create regions where physics breaks down, recognize that these represent the most extreme possibilities that theoretical physics can imagine while remaining mathematically consistent. Even the existence of small amounts of such exotic matter would create observable effects that violate fundamental principles. But cosmic scale concentrations could create regions where physical law itself becomes meaningless. But exotic matter represents just one potential explanation for physics breakdown. We must now explore how quantum field theory itself might fail on cosmic scales, creating regions where the quantum mechanical description of reality simply doesn't work. Chapter 4. Quantum Field Collapse. The breakdown of quantum field theory in the anomalous cosmic region represents perhaps the most fundamental crisis in modern physics, suggesting that the quantum mechanical description of matter and energy successful in every laboratory experiment and crucial for understanding atomic physics, nuclear physics, and particle physics might simply fail to operate correctly on cosmic scales or in extreme gravitational environments. This quantum collapse would undermine the theoretical foundation of the Standard Model and force physicists to reconceptualize the relationship between quantum mechanics and spacetime geometry. Quantum field theory describes all fundamental particles as excitations of underlying quantum fields that permeate spacetime, with particles emerging from field fluctuations and interactions governed by precise mathematical rules involving wave functions, probability amplitudes, and quantum operators. The success of quantum electrodynamics, quantum chromodynamics, and electroweak theory depends on the assumption that these quantum field descriptions remain valid throughout the universe, yet the anomalous region exhibits phenomena that seem to violate the basic mathematical structure of quantum field theory. The vacuum state, which quantum field theory describes as the lowest energy configuration of quantum fields, appears to exhibit impossible properties in the anomalous region. Normal vacuum contains quantum fluctuations, virtual particle pairs that spontaneously appear and disappear according to the uncertainty principle. But observations suggest that the anomalous region contains vacuum fluctuations with negative energy densities, imaginary frequencies, and correlation patterns that violate the fundamental commutation relations that define quantum field operators. Spontaneous symmetry breaking, the mechanism through which quantum fields acquire mass and fundamental forces differentiate from each other, appears to operate incorrectly in the anomalous region. The Higgs mechanism, which gives mass to fundamental particles through interactions with the Higgs field, seems to produce particle masses that vary chaotically across the region rather than maintaining the constant values that quantum field theory requires. Gauge invariance, the principle that ensures the mathematical consistency of electromagnetic and weak nuclear force descriptions, appears to be systematically violated in the anomalous region. Quantum field theory requires that physics remains unchanged under gauge. Transformations, mathematical changes in field variables that don't affect physical observables, yet electromagnetic and weak interaction phenomena in the anomalous region exhibit gauge-dependent effects that should be mathematically impossible. Renormalization, the mathematical procedure that removes infinite quantities from quantum field theory calculations, fails to work correctly when applied to phenomena observed in the anomalous region. Quantum field theories naturally produce infinite answers when calculating interaction probabilities and particle properties, but renormalization techniques allow physicists to extract finite, physically meaningful results. The breakdown of renormalization in the anomalous region suggests that quantum field theory itself becomes mathematically inconsistent there. The path integral formulation of quantum field theory, which describes particle behavior through summing over all possible particle trajectories weighted by quantum mechanical amplitudes, appears to produce results that violate probability conservation in the anomalous region. Path integrals that should yield total probabilities of exactly 1 instead produce probability sums that are greater than 1, less than 1, or even complex numbers outcomes that make quantum mechanical prediction impossible. Quantum entanglement, the phenomenon where particle states become correlated in ways that violate classical physics, exhibits impossible properties in the anomalous region that exceed the theoretical limits imposed by quantum mechanics. Bell's inequalities, which place upper bounds on the strength of quantum correlations, appear to be violated by factors of 2 or 3, suggesting that quantum mechanics itself underestimates the strength of quantum correlations, or that non-quantum phenomena are operating. The measurement problem in quantum mechanics, which concerns how quantum superpositions collapse into definite states during observation, appears to behave chaotically in the anomalous region. Quantum states seem to collapse into superposition states rather than definite states, maintain coherence over scales where decoherence should destroy quantum effects, and exhibit measurement outcomes that violate the Born rule for calculating quantum probabilities. Quantum tunneling, the phenomenon where particles can pass through energy barriers that classical physics prohibits, exhibits impossible properties in the anomalous region. Particles appear to tunnel through barriers with probabilities exceeding 1, tunnel backwards in time, and maintain quantum coherence during tunneling processes that should destroy coherence. These violations suggest that the Schrödinger equation itself might not govern quantum evolution correctly in the anomalous region. Virtual particle phenomena, which involve particle pairs that exist briefly due to energy-time uncertainty relations, appear to become real particles in the anomalous region without any energy source to support their existence. Virtual photons seem to propagate over distances that violate uncertainty principle constraints, while virtual particle loops contribute to interaction strengths that violate conservation of energy and momentum. The spin statistics theorem, which requires that particles with half-integer spin obey Fermi-Dirac statistics while particles with integer spin obey Bose-Einstein statistics, appears to be violated by particle behavior in the anomalous region. Fermions exhibit bosonic behavior, while bosons exhibit fermionic properties, creating particle statistics that violate the fundamental connection between quantum spin and statistical behavior. Quantum chromodynamics, the theory describing the strong nuclear force that binds quarks into protons and neutrons, fails to explain particle interactions observed in the anomalous region. Color confinement, which prevents isolated quarks from existing outside hadrons, appears to break down completely, allowing free quarks and exotic color combinations that violate asymptotic freedom and other fundamental QCD principles. The standard model Lagrangian, which encodes all known particle physics through a mathematical expression describing particle interactions and field dynamics, produces incorrect predictions for every observable quantity in the anomalous region. Coupling constants take impossible values, mass terms exhibit chaotic behavior, and interaction terms violate gauge invariance and renormalization requirements. Quantum corrections to general relativity, which should remain small except at the Planck scale, where quantum gravity becomes important, appear to dominate classical gravitational effects in the anomalous region. Quantum gravitational phenomena that should be utterly negligible at cosmic scales seem to override classical spacetime curvature, suggesting that the semi-classical approximation breaks down completely. Vacuum polarization effects, where electromagnetic fields create virtual particle pairs that modify the properties of spacetime and electromagnetic fields, exhibit impossible magnitudes in the anomalous region. Instead of tiny corrections to electromagnetic interactions, vacuum polarization appears to create macroscopic effects that violate energy conservation and electromagnetic field equations. The Casimir effect, where quantum vacuum fluctuations create measurable forces between conducting surfaces, exhibits anomalous behavior that violates quantum field theory predictions. Casimir forces appear to operate over cosmic distances with strengths that should be impossible according to quantum field theory, suggesting that vacuum energy itself behaves differently in the anomalous region. Hawking radiation, the quantum mechanical process that causes black holes to evaporate through particle creation near event horizons, appears to operate incorrectly in the anomalous region. Black holes seem to accrete rather than evaporate. Radiation temperatures violate thermodynamic relationships, and information paradox behaviors contradict quantum mechanical unitarity requirements. Quantum field theory in curved spacetime, which describes quantum mechanical phenomena in gravitational fields, completely breaks down in the anomalous region. The stress-energy tensor that describes matter's gravitational effects becomes mathematically ill-defined. Field equations produce infinite or imaginary results, and the relationship between quantum mechanics and gravity becomes completely incoherent. The holographic principle, which connects quantum field theories to gravitational physics through higher dimensional correspondences, fails to work correctly when applied to the anomalous region. Holographic dictionaries that should relate quantum field phenomena to gravitational dynamics produce inconsistent results, suggesting that the fundamental relationship between quantum mechanics and gravity breaks down. As you contemplate the complete breakdown of quantum field theory in the anomalous region, recognize that this represents more than a challenge to current understanding. It suggests that the quantum mechanical description of reality itself might be fundamentally limited or incorrect. If quantum field theory fails on cosmic scales, then the theoretical foundation of modern physics requires complete reconstruction. But quantum field theory breakdown represents just one aspect of physics failure in the anomalous region. We must now explore how spacetime geometry itself might become ill-defined, creating regions where the concepts of space and time lose their fundamental meaning. Chapter 5: Spacetime Geometry Failure. The most terrifying aspect of the anomalous cosmic region might be the apparent breakdown of spacetime geometry itself, the fundamental mathematical structure that defines space, time, and their relationship through Einstein's general relativity. In this region, the concepts of distance, duration, causality, and geometric relationship appear to become undefined or chaotically variable, suggesting that the fabric of spacetime operates according to principles so alien that the basic framework of physics becomes meaningless. Einstein's general relativity describes gravity as curvature of spacetime geometry, where massive objects create distortions in the four-dimensional continuum of space and time that determine how matter and energy move through cosmic space. This geometric description has passed every experimental test and successfully predicted phenomena from planetary orbital precession to gravitational wave propagation. Yet the anomalous region exhibits gravitational effects that seem to require space-time geometries that violate the mathematical consistency of Einstein's field equations. The metric tensor, which defines distances and time intervals in curved spacetime, appears to take impossible values in the anomalous region that violate the mathematical requirements for spacetime geometry. Normal spacetime metrics must be symmetric, invertible, and possess specific signature properties that distinguish space from time dimensions. Observations suggest that the anomalous region contains metrics with asymmetric components, non-invertible configurations, and signature changes that should be mathematically impossible. Causal structure, which defines the relationship between events in spacetime and determines which events can influence which other events, appears to break down completely in the anomalous region. The light cone structure that separates past, future, and space-like separated events becomes ill-defined when space-time geometry fails, creating regions where effects can precede causes, where information propagates instantaneously, and where temporal ordering becomes arbitrary. The Einstein field equations, G = 8T, which relate space-time curvature to matter and energy distributions, appear to have no consistent solutions when applied to the anomalous region. The left side of the equations describes geometric curvature, while the right side describes matter-energy content. But observations suggest matter-energy configurations that produce curvature tensors with impossible mathematical properties, including negative eigenvalues, non-real components, and undefined derivatives. Geodesic motion, which describes how particles move along curved spacetime trajectories in the absence of non-gravitational forces, becomes undefined when spacetime geometry breaks down. Particles in the anomalous region exhibit trajectories that don't correspond to geodesics of any consistent metric, suggesting that the concept of straight-line motion in curved spacetime becomes meaningless when geometry itself fails. Coordinate systems, which provide mathematical frameworks for describing spacetime positions and relationships, cannot be consistently defined throughout the anomalous region. Normal spacetime allows multiple coordinate systems related by smooth transformations, but the anomalous region seems to contain singularities, discontinuities, and topological defects that prevent the construction of well-behaved coordinate systems. Curvature tensors, which mathematically describe how spacetime geometry deviates from flat space, exhibit impossible properties in the anomalous region, including infinite components, imaginary values, and discontinuous behavior that violates the differential geometric foundations of general relativity. The Riemann curvature tensor, which contains all information about spacetime geometry, becomes mathematically ill-defined. Topological properties of spacetime, which describe global geometric features like connectivity and boundary structure, appear to change chaotically throughout the anomalous region. Spacetime topology should remain constant except during quantum gravitational processes at the Planck scale. Yet observations suggest macroscopic topology changes, including wormhole formation, spacetime foam structure, and non-trivial connectivity patterns. The equivalence principle, which states that gravitational acceleration is locally indistinguishable from acceleration due to other forces, fails systematically in the anomalous region. Different types of matter exhibit different accelerations in gravitational fields, violating the foundation of general relativity and suggesting that gravity itself operates according to different principles in that cosmic region. Tidal effects, which describe how gravitational fields vary across extended objects and create stretching forces that can disrupt matter, exhibit impossible properties in the anomalous region. Tidal forces appear to strengthen objects rather than disrupting them, create attractive effects between objects that should be repelled, and operate over distance scales that violate the inverse cube relationship of normal tidal physics. Parallel transport, the geometric procedure for comparing vectors and tensors at different spacetime points becomes undefined when spacetime geometry breaks down. Physical quantities cannot be consistently compared between different locations in the anomalous region because the geometric structure needed for such comparisons doesn't exist consistently. Horizons and causal boundaries, which define regions from which information cannot escape or beyond which information cannot penetrate, exhibit chaotic behavior in the anomalous region. Event horizons appear and disappear randomly. Apparent horizons move in ways that violate general relativity, and particle horizons expand and contract in patterns that violate cosmological evolution models. Spacetime singularities, where curvature and matter density become infinite and physics breaks down completely, appear to exist throughout the anomalous region rather than being confined to black hole centers or cosmic origins. These naked singularities violate cosmic censorship principles and create regions where general relativity provides no physical predictions. Conformal structure, which describes angle relationships and light propagation in curved spacetime, becomes undefined in regions where spacetime geometry fails. Light rays cannot propagate consistently through the anomalous region because the null geodesics that define light ray paths require consistent metric structure that doesn't exist. Killing vectors and symmetries, which describe spacetime configurations that remain unchanged under specific transformations, exhibit impossible properties in the anomalous region. Symmetries that should be exact become approximate. Conserved quantities associated with symmetries become non-conserved, and the mathematical structure that connects symmetries to conservation laws breaks down. The stress-energy tensor, which describes matter and energy distributions that create spacetime curvature, takes impossible values in the anomalous region that violate energy conditions and produce curvature tensors with pathological properties. Energy densities become negative, pressure components become imaginary, and momentum flux violates conservation laws. Cosmological models, which describe spacetime evolution on universal scales, cannot be consistently extended through the anomalous region. The Friedmann equations that govern cosmic expansion produce undefined or imaginary solutions when applied to matter distributions observed in the anomalous region, suggesting that cosmic evolution itself breaks down. Quantum gravitational effects, which should remain negligible except at microscopic scales, appear to dominate classical geometry throughout the anomalous region. Spacetime foam, virtual black hole formation, and topology fluctuations that should occur only at the Planck scale seem to operate on cosmic scales, suggesting that the semi-classical approximation completely fails. Gravitational wave propagation, which should follow null geodesics through curved spacetime at the speed of light, exhibits impossible behavior in the anomalous region. Gravitational waves appear to propagate faster than light, slower than light, or along paths that don't correspond to any consistent spacetime geometry, violating the wave equation and geometric optics. Frame dragging effects, where rotating massive objects drag spacetime geometry and affect the motion of nearby objects, operate incorrectly in the anomalous region. Spacetime appears to rotate independently of matter rotation, creating gravitomagnetic fields with properties that violate the geometric relationships of general relativity. Cosmological horizons, which define the maximum distance from which light can reach observers during cosmic expansion, exhibit chaotic behavior in the anomalous region. Particle horizons and event horizons fluctuate in size, change position arbitrarily, and violate the causal structure that cosmic evolution models require. As you contemplate the breakdown of spacetime geometry itself in the anomalous region, recognize that this represents the most fundamental crisis imaginable in physics. If space and time cease to operate according to comprehensible geometric principles, then the basic framework within which all physical phenomena occur becomes meaningless, making scientific description and prediction impossible. But space-time geometry failure is just one aspect of the physics breakdown in the anomalous region. We must now explore how the fundamental constants of nature, the numbers that determine the strength of forces and the properties of matter, might vary in ways that make stable atoms, chemistry, and life impossible